Set up my stuff.
So I try my best to let those people who's waiting on the waiting room as much as possible, but like, yeah, sometimes I miss them. So I will try my best.
Okay, thank you. Thank you. You were on top of it last session. I guess it's 2:55. Shall we start?
I think so, yeah.
Okay. So yeah, welcome everyone to the second air quality session with the linkages to weather and climate. In the interest of time, we'll just get started right in. So if Nazrul, if you want to share your screen. So our first speaker, Nazrul Islam, talking about satellite-based methane emission estimates for Western Canada using a mass balance method.
And just so people know, I'm going to be running the clock as soon as you start speaking, and I'll give you a warning when we've got 3 minutes left, and another one when we've got about 30 seconds left, approximately. Okay.
Okay.
So go ahead, Nazrul.
Are you hearing me well?
Yeah, please.
All good.
All good. Start up.
Okay. Hello, everyone. This is Nazrul Islam. Currently, I'm working as a postdoc at Global Monitoring Laboratory at NOAA. And also, my employment is part of the Cooperative Institute for Research in Environmental Science at University of Colorado Boulder. The topic that I'm going to cover is part of my PhD work. I did my PhD from University of Northern British Columbia under the supervision of Professor Peter Jackson. So before starting my talk, I would like to acknowledge Professor Peter Jackson for his guidance. I would also like to acknowledge UNBC and Compute Canada SPC facility, especially for Compute Canada, where I perform my geoscam simulation. So I think you're familiar with this left-hand side figure. For the second year in a row, NOAA scientists observed a record annual increase in atmospheric level of methane, a powerful heat-trapping greenhouse gas that is second largest contributor to human caused global warming after carbon dioxide. NOAA's preliminary result showed that annual increase in the atmospheric methane during 2021 was 17 ppb, the largest annual increase recorded since systematic measurement began in 1983. The increase during 2020 was 15.3 ppb. There are a variety of methane sources, including both anthropogenic and natural sources, which is a wetland. And there is an ongoing debate for determining the main driving factor for increasing atmospheric methane. Methane has relatively short lifetime in the atmosphere. Recently, climate experts and diplomats have put extra emphasis on controlling methane emissions because it is relatively easy to reduce emission by stopping methane escaping from oil and gas wells and leaking from pipeline. So, Canadian government is also doing the same things for methane emission reductions. They promised to reduce 40 to 50% methane emissions reductions from oil and gas sector by 2025 from the level of 2012. As shown in this figure, by the blue lines, the historical methane emissions peaked in 2014 and subsequently declines for the rest of the historical period up to 2018. Historical decline in methane emissions are mainly attributed to reductions in banting and flaring in response to provincial requirements. The regulatory scenario, which is represented by the red line, indicates the model methane emission based on regulatory regimes in place in Western provinces. Note that Western provinces, especially British Columbia, Alberta, Saskatchewan, Manitoba, representing more than 90% of oil and gas associated methane emissions. Implementation of methane regulation are modeled to lead to decline in methane emissions from 2022 to 2025. Overall, federal and provincial methane regulation alone are modeled to achieve methane emission reductions of 39% by 2025 relative to 2012 levels. Therefore, we conclude that Canada is on track to meet the 2025 target for methane emission reductions from the oil and gas sector. However, several recent studies identified government inventories largely underestimating methane emissions, mainly due to methodological issues. The government also recognized this. Therefore, it is important to verify government progress towards methane emission reductions goal. So, in the subsequent slides, I will briefly introduce the GOSIT data products, their validation implementation of the GOSIT data products in a mass balance technique, which are used for quantifying methane emissions from oil and gas sector. I also use Geoscam's simulated methane products in the same mass balance method. After introducing the techniques, I will show you my significant results and comparison with recent studies. Finally, I will give you a summary of my talk. So in this study, we use the latest available GOSIT methane datasets. There are two products which are used in the analysis, that is OCPR version 9.0 and SRPR version 2.3.9. And both products are based on proxy retrievals. I will not go into details about the retrieval algorithm for each product. The OCPR product is based on inversible ester, and SRPR is based on Remutec, which produced by the Sean. So in a recent study, we found reasonable agreement between GOSIT OCPR data products and the independently measured high quality aircraft and TCON data products, which allowed us to use GOSIT data products for methane emissions estimated from 2009 to 2019 in Western Canada. We also performed an elevation correction and latitudinal bias correction for each GOSIT observation before applying GOSIT data in the mass balance technique. The latitudinal bias correction is very important because we are setting in the kind of high latitude area, so there is some bias in the latitudinal. So we have to consider bias correction for these things. So before applying GOSIT data into the mass balance method, we draw annual average GOSIT methane map at 0.5 degree by 0.5 degree resolution, overlaid with the geographical distribution of facilities to determine the source area. As shown in this figure, elevated methane appeared over the oil and gas facilities areas in Western Canada. We found similar observation for other years. So we use the red polygon as our source area and black polygon for our surroundings area. Methane enhancements for the mass balance technique, which is the key, and is quantified by subtracting median value of methane in the surrounding regions from the median value of the source region. We found also similar feature from our Geoscam simulated methane data products, which is shown in the right-hand side. Therefore, we also apply the mass balance technique on Geoscam products to validate GOSIT data-based quantity. Once we have methane enhancements, we quantified emissions by multiplying enhancements with the conversion factor. The conversion factors include several terms. For instance, M, which is a constant factor required to convert a methane mole fraction change to a methane mass change per area at standard condition. MEXP is a dimensionless factor applied to correct for actual mass. L is the length of the source area. C is also a constant factor, and B is the pressure weighted average boundary layer wind speeds. So we quantified emissions for two GOSIT products, and emission quantities that are presented in the subsequent slides are based on the average of this two data products. The uncertainty of emissions is calculated as the sum of quadrature of uncertainties associated with enhancement and wind. So we quantified methane emissions using GOSIT products for the year from 2009 to 2019. The quantities from previous equation are representing total methane emissions, which includes both anthropogenic and natural sources. To compare our results with other data sets, we estimate annual total emissions by adding Edgar version 6 total anthropogenic emission and Western wetland products, which is, I used the recent Western product that is 1.3.1. And this Edgar plus wetland products is represented by the yellow bar in this figure, satellite total by the blue bar, and the geoscam is by the red bar. Note that the geoscam simulation from 2000, we did geoscam simulation from 2010 to 2017. That's the, you didn't see the geoscam bar in 2009 and after 2017. So we found very consistent results. Overall trends are also very encouraging. So for instance, ghosted overall mean is 8.40 teragram per year. And our Edgar and geoscam base are also around, for geoscam is 8.8, and the Edgar plus wetland is 8.16. The overall mean from 2009 2019. So now we are trying to estimate the contribution only from oil and gas sources in Western Canada. For this purpose, we subtracted the Edgar non-oil and gas anthropogenic total and Western wetland from the satellite-based total emissions using that equation. Therefore, the residuals are the oil and gas contribution. Also note that our source area extended to Montana and North Dakota of USA. So to represent oil and gas only from Western Canada, we again subtracted relevant oil and gas quantities from these two states. We used latest literature to quantify oil and gas associated emissions from Montana and North Dakota. So we found very interesting results. Edgar and government inventories are almost identical, but our mass balance based quantities are in overall 60% higher than government based quantity. Another interesting feature, excuse me, another interesting feature about the trend. As mentioned at the beginning of my talk, government inventory indicated oil and gas emissions are getting lower after record high in 2014. The overall trends from our results also indicates the same thing, which is very promising. However, we are not 100% sure whether the trend are associated with policy relevant reduction or price relevant less growth during that time. We need further investigation and analysis for further years. So now we compare our satellite-based oil and gas emissions with recent relevant literature. We chose 3 relevant studies, which are also very recent and representing almost similar period of analysis. For instance, Berry et al. And Lowe et al. Used co-set observation and surface network observation in inversion platform for emission quantities. Chan et al. Used surface network only. Our mass balance based anthropogenic quantities is almost identical to Berry et al., which is around, our estimated anthropogenic emissions is around 4.6 teragram per year.
Just a quick note, we're at the 3-minute mark from the end now. Just let you know. Thanks.
Yes. Our overall mean oil and gas quantities are 3.5 teragram per year and are also close to other oil and gas quantities investigated by Chen et al. And Lowe et al. So from our results and compared with other studies, we found our mass balance based approach is enabled to consistently quantify oil and gas methane emissions in Western Canada. We also found government estimated emissions are underestimating the emissions quantities. We found downward emissions trend after 2014, which is also appeared in government quantities. Although the trend after 2014 is promising, we are not sure the trend is associated with policy relevant emission reduction. So investigation after 2019 is required when major policies have been in place in Western Canada. So our future studies also use the Tropumi methane data products. So I think we'll get some promising results of 2019 using Tropumi data. So thank you very much.
Okay, thank you. So we have about 1.5 minutes here for questions from the audience. If you have a question.
you mind if I ask,
Go ahead.
Azrael? I didn't quite catch how you calculate your delta methane. Was that sort of the in the upwind to the or sorry, downwind to the east minus the upwind to the west total column, or?
Yeah, it is based on total column. So so in this figure, so the red polygon is for the source area and the black polygon for the surrounding area. So we quantified the median XCS4 for the black rectangle area, excluding the red polygon, and then I subtracted the median from the source rectangle.
Okay.
And we use the kind of boundary layer height wind speed in the mass balance equation.
That was my next question. Thank you.
Okay, I think we should move on to the next speaker then. Over to you, Mark.
Yes. Oh, yeah, absolutely. Thanks, Paul. Yeah, so our next speaker is, thanks again, Nazar.
Thank you.
Our next speaker is Robin Stevens from U Montreal, talking about sensitivity of air pollution in Quebec to regional emissions in meteorology. So whenever you're ready. Do you want to do a sound check? We can't hear anything at the moment.
You may be muted, Robin.
Oh, you're, yes, sorry, there you are. I see a mute. I see a mute symbol.
Here we go.
Great.
My apologies.
Yes, now we can hear you. Okay, go ahead.
All right. Before I get started, I'd like to acknowledge the contributions of my co-authors on this project and that we have gained funding support from the Ministère de l'Environnement et de la lutte contre les changements climatiques. So the problem that we're investigating in this project is where is the pollution in the air pollution in Quebec coming from? Is it coming from local sources or transport from Ontario or transport from the United States? And of course, it's all of these sources, but we'd like to be a bit more quantitative about how much from each of those. And we also wanted to investigate how that's going to change in the future. So I'm going to be heavy on talking about my methods in this talk. It's because this is a project in 3 parts. The first is to run the GeoSchem chemical transport model and to get concentrations of different air pollutants, including ozone and particulate matter and NOx. The second is to create a set of statistical models that capture the change in these concentrations based on changes in meteorology. And then the third is to use output from regional climate models together with these statistical relationships in order to predict how these concentrations of pollutants might change in the future based on changes in climate alone. So going through those in more detail, step 1 is to run GeoSchem. So I'm doing this for 4 or 5 year period spanning from 1980 to 2015. The reason that we're not doing one continuous run is just to be more efficient with our resources. But importantly, the anthropogenic emissions are always from the year 2010, because remember, we're trying to link concentrations to changes in meteorology, and we don't want a convolution with changes in emissions over that same time period. I'm also doing 3 sensitivity studies with this as I go, where I turn off anthropogenic emissions from 3 regions. First, we turn them off from the province of Quebec itself. Second, we turn it off from everywhere else in Canada except for Quebec. And in the third sensitivity study, we turn off anthropogenic emissions from the USA. And so we can get some interesting results just based off of the simulations on their own. Due to time constraints, I'm going to focus on summertime ozone, but I could do similar kind of analysis looking at the other pollutants and for the entire year. So on my top row, I'm showing the absolute difference in summertime ozone, and the bottom, the relative difference in summertime ozone off of my model domain. Because ozone is a secondary pollutant, which is formed in the atmosphere rather than directly emitted, we see that the local contribution to the pollutants is not as strong as it is for other air pollutants like particulate matter and NOx. while emissions from the rest of Canada, besides Quebec, have this wide-ranging effect on ozone. And actually, the strongest magnitude of change on summertime ozone in particular is coming from emissions from the United States, which reaches up to 7 ppb close to the border with the United States. But that was just the simulations on their own. And that brings us to the second step of this project. So we're following a methodology that was described in Chen et al. Of 2017. And the essential part of this is that we're doing a linear regression with respect to a few different meteorological variables, which include temperature, precipitation, surface pressure, and wind speeds, all at or near the surface. It's not just the linear regression versus the meteorology in the grid cell itself, though. We also want to capture the effects of more mesoscale systems. But to do that, we need to do some kind of dimensionality reduction. And we're using singular value decomposition in order to do that. I'm going to talk about this a little bit more later, but the essential point here is that it's a way to capture this multi-dimensional data of how meteorology in surrounding grid cells is related to the pollutant concentration in this grid cell itself. The other thing I'd like to highlight is that we're making independent statistical models of meteorology connected to air pollutant concentration for each month independently to isolate seasonal cycles. And we're doing this for each grid cell, and we're doing this for each of the 4 scenarios. So I'm going to show some preliminary results. This is only from 2010 to 2013 because I don't have sufficient data yet, but I can at least explain my methods well with them. And to start with, I'm going to show the correlations of these meteorological variables with the July ozone over our model region. And what comes highlighted most strongly here is that the surface temperature over land is strongly correlated with the ozone concentration, which makes sense because in July we expect that the photochemistry is going to be driving ozone formation, and sunny days are also going to be hot days. So it is quite expected that surface temperature and ozone concentration would be correlated in each of these horizontal grid cells over land. So if we did the linear regression based off of these alone, it would be strongly dominated by the surface temperature. What we want in addition to just regression versus each of the variables is this singular value decomposition. So I'm going to focus in on just one grid cell instead of the whole domain. I'm choosing Montreal because that's where I am, and to try and explain this method. So I mentioned that this was a method of dimensionality reduction. So for the time series of each of our meteorological variables in each of these grid cells that I'm showing, the way that this works is we multiply them by the spatial weight in that grid cell and multiply it by the variable weight for that variable. And then add them all up together, and this gets us a single time series, which we can then use in our linear regression. So the first component of our singular value decomposition, really there's 5, but I'm only using 2, so I'm only showing 2, has this really homogeneous spatial weights. And you can see that temperature has this negative weight and spatial weights are negative. So a negative times a negative is a positive. So we get a positive relationship between the temperature in all of these grid cells all around here and the ozone in this one grid cell and where Montreal is. So what this first component has given us has essentially been the autocorrelation of the meteorology with itself. If the temperature is high in this grid cell, the ozone is high in this grid cell. And if the temperature is high in this grid cell, the temperature tends to be high in all of the grid cells around it. The second component is giving us more interesting, different information. So what I can highlight here is that a positive sea level pressure multiplied by negative here. So we have negative pressure, surface pressure up in the northwest and a positive surface pressure in the southeast, along with positive precipitation in the northwest and negative precipitation in the southeast, is associated with high ozone here. And my interpretation of this is that if we have a storm that's passing over to the northwest of Montreal, that changes the circulation pattern in such a way that we have more ozone formation in Montreal itself. And this is really the kind of pattern that we're trying to capture with the singular value decomposition, not just for Montreal, but for every location in our domain. In order to make the information presentable, I'm going to stick with just Montreal as opposed to showing the entire domain, and show for our 4 years for July. So these are 4 July's daily data. What GeoSChem predicts is in blue, and what our statistical fit is showing in orange here. This is the actual equation that's being used for this grid cell. And we get a good correlation coefficient of 0.74 for this grid cell for ozone based on this data. What I'm showing on the bottom plot here is a normalized temperature for the same period, just to show that if you look by eye, the temperature is highly correlated with the ozone. So that's a large part of the fit for what's being captured by the statistical model for this grid cell. So step 3, once we have a statistical fit that we're confident in capturing actual patterns of meteorology and air plume concentrations for the entire period as opposed to the shorter period, we will then apply it to regional climate model output for both a middle of the road scenario and a business as usual scenario, as well as the historical period. And then by comparing the output of the statistical model for these futures and the historical period, we can estimate how climate change is going to affect these plume concentrations in the future. And further, I only showed one model for time's sake, but we're going to make these for each of the scenarios where we remove anthropogenic emissions from each of these regions, from Quebec, from the rest of Canada, and from the United States. And they'll give us different predictions of what the air plume concentrations in the future will be. And so using those, we can look at how transboundary transport of pollution to Quebec might change in the future. So I've got some very, very preliminary results of this using this preliminary statistical fit. And I'd like to emphasize that this is just a proof of concept that I'm showing. So for a single model with an RCP 8.5 scenario, I have here this July ozone. This is daily data, but it runs for all the Julys between 2006 and 2100. And I'm showing what the ozone concentration predicted by the same statistical model that I showed a few slides ago would be, or rather the statistical models for the 3 scenarios with no emissions from the United States, or no emissions from Canada, or no emissions from Quebec. And I'm showing the normalized meteorological variables on the bottom plot here. So you can see in red that the temperature is increasing with time, as we would expect it would under a business as usual climate change scenario. And while it's more difficult to see because of the relationship between the ozone and the temperature, the ozone in all 3 scenarios is rising slightly, though it is hard to tell apart from the daily variability. What's more, the 2 scenarios that include emissions from the United States are a bit more sensitive to temperature than the United States, the case without emissions from the United States. So again, it's difficult to see, but trust my word that in these results, they are increasing a little bit further. But once again, these results are preliminary, and I don't know if this is going to be a robust feature in the final results. And with that, I'm going to come to my summary slide. So we're running GeoSChem. We are finding statistical relationships between the meteorology and air pollution. And then using those relationships, we're making predictions of how pollution might change in the future. And I'm going to leave this slide up while I take questions. So thank you for your attention.
Great. So I think we've time for a question or 2.
Hi, Robin. Nice presentation. I have one question about your statistic relationship model. I'm wondering, is the regression coefficient sensitive with time? because I think you conduct regression for each grade point and also for monthly mean data, right? But what if we change the period of the regression model? Will it be sensitive to, will the regression coefficient be sensitive to the time you study?
So I just want to correct one point in your question that we're not using the monthly mean, we're actually using daily mean data. But we are making a independent statistical model for each month. So I'm sure that the answer to your question is yes, but because I've only got the 4 years of data, I haven't investigated that yet. It would have to be, I think the more appropriate thing to do would be to compare something like the 1980s versus the 2000s to see if those relationships are different. But any correlation that I was showing right now is for the entire time series.
Okay,
Yes.
thank you. Thank you, Robin. I think we should probably move on and just try to keep an eye on the clock here too. So who's next, Mark?
So yeah, next speaker is Roya Karamen, if I said that right, from Environment Canada, talking about representation of, oh, sorry, it's a little different, partitioning of rain and snow and new parameterization for below cloud scavenging, size resolved particles by rain and snow. Thanks. Go ahead.
Hi, thank you everyone. So today I'm going to talk about partitioning of rain and snow, and also I have some results from new cloud scavenging of particles by rain and snow in GenMac. So as you know, for aerosol, we have this scavenging in cloud.
Roya, a quick comment. Can you access display settings and change it to presenter view? Thank you. Swap. Excellent. Yes, do that.
Sorry. Thank you for that.
Okay, go ahead.
So we have the scavenging of particles in cloud and also below cloud scavenging. For this study, we focus on below cloud scavenging. And for below cloud scavenging, which includes the removal of particles in the atmosphere, there are many different processes, and including this scavenging in models is difficult. Some of the processes are like Brownian motion, turbulent, shear diffusion, and many other processes. And the uncertainties in models for theoretical formulation is 1 or 2 orders of magnitude for rain or liquid scavenging, and for solid scavenging, it's more difficult, up to 3 orders of magnitude. And the reason is that for snow scavenging, there are very different types and size of snow particles, and it's more difficult. In GenMac, what we have currently for below cloud scavenging is based on SNE 1984, and it's based on precipitation rate and mean collision efficiency. You can see the formulas here for rain and for snow. They are different, and for snow, we have a slightly difficult formulation. It depends on the size of rain droplets or the snow particles and precipitation rate. For this study, we have included semi-empirical parameterization for snow and rain scavenging, which is based on Born 2014. And you see the formula here. It depends on R, which is precipitation intensity, and A and B are the coefficient. Just to have an idea, they are depending on rain or snow particles size, and also the phase of precipitation. So we are trying the semi-empirical scavenging for rain and snow as well. And to see the difference between SNE 1984 and Born 2014, we have 2 panels here. The left panel shows the rain or liquid phase, and the solid line shows a high intensity of liquid precipitation, and the dashed line shows the low intensity. for seen in blue color and one in red color, we see that for lower intensity of precipitation, they are almost the same and they overlap. But for higher intensity, we see that two scavenging scheme differ, and mostly for particles smaller than 1 micron. For the snow or solid phase, we see different pattern, and for lower intensity, they are different for particles below 1 micron, and for particles larger than 1 micron, they differ for higher intensity. So the point here is that scavenging by rain and snow are different, and also the order is different too. And the other point that we are trying to try in this experiment is treatment of liquid and solid precipitation. In GEMMAC and in many other models, there are just a single phase for each location, and depending on temperature, they find liquid or solid phase. For example, in GEMMAC, if it's above 0, it's going to be liquid phase, and if it's below 0, it's solid or snow, which is not what happens in reality. Sometimes liquid and solid phases coexist, or the phases will be to have the phases consistent with the GEM prediction. We are including the partitioning, and we are using the precipitation partitioning from GEM microphysics. And we know that the scavenging efficiency is different for rain and snow, so to have a reliable model prediction is essential to do this partitioning. And the plots here, the left panel shows the temperature, the red color shows above 0, which is rain, and the blue color shows colder than 0, which should be snow. But in reality, you see that for solid and liquid fluxes, we have both phases. And just before showing the result, it is the last slide to have some background about GEMMAC model, which is Environment Climate Change Canada's Air Quality Prediction Model. And for this study, I have 3 model experiments conducted for April 2018, which we have observation results as well. And the map here that you see, the blue color shows 10 kilometers and the red color is 2.5, 2 different domains that we have. And the blue dots show the station or observation station for precipitation samples. And the first experiment is base case. It's what we have default in GEMMAC. It's based on, it's in 1984, and also we have a single phase depending on temperature. For the second experiment, we have partitioning of rain and snow. And for the last one, which includes partitioning as well, it is based on 2014, and the scavenging scheme is replaced with 2014. This slide shows some wet fluxes. The results, the upper panels are net differences between rain and snow partition experiment and also base. And for nitrogen species, the 2 first panels, the upper panels, you see that we have both increase and decrease, and the result is mixed. But for sulfide, you see that the blue color is the dominant, showing that the wet fluxes is decreasing by including partitioning of rain and snow. And the reason is maybe including partitioning leads to higher snow scavenging, which decreases the scavenging of SO2 in gas phase and sulfide in liquid phase. And the last panel, upper panel, shows sulfate in aqueous phase, which red color is dominant. We have blue color as well, but by including rain and snow and increasing the snow during April, we see that scavenging of sulfate particle increases as well. The lower panel shows the net difference between 2014 scheme and partition experiment. And we see that, again, there are mixed results, increase and decrease of scavenging depending on the location and the phase. And for the sulfide, again, the blue color is dominant, but the magnitude is lower than the upper panel. We compare GeoMax simulation with observation, and we have different styles, Capmon, Alberta, NAPS. But for this presentation, I've included just example of APQMP or Alberta precipitation sites. We compared GeoMax and observation. In the upper panels, they show precipitation. We don't expect to see difference between different experiments for precipitation. However, for lower panels, which are sulfate, we see a slightly different result, and you see the result, statistical result in each plot as well. For example, comparing R, which is correlation coefficient, shows that by partitioning, or the second experiment here, shows slightly improvement and compared to base study, and then 2014 shows the best result between experiments. Or comparing normalized mean bias shows that for two experiments, rain, snow, and 2014, we have improvement or better result compared to the base study, and there is a negative bias. And for factor 2, again, we can see that 2014 experiment has the best result. So in short, for sulfate, we see that 2014 is the best experiment that we have. The same plots for nitrate and ammonium shows that we see improvement for correlation coefficient. However, for nitrate, we don't see improvement. They are slightly higher, or because it's negative, lower numbers. But for factor 2, again, we see improvement by 2014. That is the summary of the result here. And for ammonium, the lower panels, again, comparing R shows they are almost the same. And for factor 2, 2014 again wins and has the best results. And here we have GeoMax simulation for aerosol. The left panels are base study, base case for April. So they are average for April, and they include particle sulfate, nitrate, and ammonium. And the middle panels are the net difference between rain and snow and base, and the right panels are 2014 versus the rain and snow. And for the middle panels, we see that including partitioning again leads to increase of sulfate particles. We have red color here. And for ammonium as well, we have red color is the dominant one. But we have some blue color as well, especially for the oil sand region. And for nitrate, the middle panel, we have both increase and decrease. By including partitioning of rain and snow or precipitation phase, we have higher particles in the atmosphere and less scavenging of particles, sulfate and ammonium. And for the last panel or right panels, we see that using 2014 leads to both increase and decrease of particle concentration in the atmosphere, or it depending on the location, the scavenging of particles increase or decrease. And we have PM 2.5, particle width size 2.5. Again, we have base in a left-hand side, and we can see that by including partitioning of precipitation phase, rain and snow, we have higher particles, or the red color is the dominant one for PM 2.5. And comparing the 2014 and rain and snow shows that it can be increased or decreased again. So in summary, it is very important to have partitioning of precipitation phases to have accurate results from the model. And we included precipitation partitioning in GeoMax. And by including precipitation partitioning, we have the same phase from GEM. And when we compare with observation, we see that partitioning in general leads to better results compared to base case. And by including precipitation partitioning, we also saw that we have lower refluxes of sulfur species in general, which leads to higher concentration of sulfur particles in the atmosphere. And we also included a new scavenging scheme around 2014, which is semi-empirical. And comparing to a SNE scheme, we saw that we have better results. And when we have observation in general, we see that one scheme shows better result than a SNE scheme, and also partitioning, only partitioning. So that's the last slide.
Thanks, Rob. Very interesting. I will point out there was a 25-minute slot given to you on the schedule, which apparently wasn't communicated. I don't know how that was supposed to happen, but we have lots of time for questions as a result of that miscommunication. But yeah, if we could start with some questions and maybe get a discussion going, because we've got 10 minutes before we have to start the next talk. I could start. I'm curious, the parameterizations for scavenging based on the particle size.
Yeah.
You can get a sense of the uncertainty just from those two models and the differences between them, but is there some measure of the uncertainty for those, like beyond just comparing the two? Like, do the themselves give
Yes.
much?
So there are many studies like to compare different uncertainties. In the first slide, I mentioned few processes that they are not easy to include all of this in models. So there are some papers just to compare the orders of these uncertainties for rain and snow. And for this one 2014 that I have here, they compared the different models. So they saw better results for lower uncertainties compared to just theoretical formulas. So they have observation as well. It is based on observation as well.
Okay. And then I'm sure the observations have a wide range of variation as well.
Yes, yes. So it is not the perfect method, and also for this, they have some assumption as well, which increase the uncertainties. But again, compared to the scene that we have in GEMAC, we see better result.
Can I ask a question about Robin's talk?
Oh yeah, okay, sure. Yeah, we got some open time, so.
I think there was assumption there that the emissions don't change. So what happens in the likely scenario that emissions are going down?
Yeah, so we specifically set up the experiment with the emissions not changing in order to isolate that from the effects that we are interested in. So I won't be able to say anything quantitative, partially because our results aren't finished yet, but also because it's not something that we're directly investigating. But yeah, for the example that I showed, assuming that this relationship between ozone and temperature is robust, which in itself there's reasons to question whether it was. If that's true and the emissions are going down, then those two effects are going to cancel each other, and it's going to take more analysis than I've done here to find out which of those is stronger. But you know, I would guess that the emissions going down would be the stronger effect.
Any questions for either Roy or other speakers?
I'm also seeing in the chat, Rachel was kind enough to point out that there is supposed to be a 10-minute health break. So I apologize. I was not made aware of that.
Okay.
But
So Ryan's talk was the right length.
yeah,
Okay.
so in our previous session, the talk went for 20 minutes, so it made sense.
We will get going again with the rest of the talks at 3:50 though. I had a question for Robin as well, and that was with regards to the singular value decomposition. The images that you're showing looked like they're about a 10 by 10 grid out of the total grid that you had. And I was wondering if there's limitations on the methodology because you're doing a matrix inversion somewhere along the line, I'm assuming there, but how large a domain can you operate that kind of setup on?
I think that the limitation is mostly on the computing power available to us, and we can go larger than 9 by 9. That was mostly an example, and
Sure.
I don't know if I'm going to stick with that size or not.
Okay. I was wondering how it scaled, with number of grid points effectively.
I mean, in terms of efficiency of how long it takes to do it, I'm sure it goes by the square or something similar, but the other limitation is that the more grid points that you use around it, the more of the boundary you have to exclude from the analysis, because you can only do this analysis if you've got a center point that's got that many cells over in order to use in the singular value decomposition.
Okay. So I see we have another question from Roya from Juan Yu, who asks, I wonder does the precipitation duration length play a role in below cloud? If you look in the chat window, you can see the original question.
Oh, yeah. I was trying to ask one question for Robin, but I will do it later.
Okay. So, Roya?
So for the answer, we don't directly include the time or the duration of precipitation in formulas that we have for model. So this scavenging we don't include. So it depends on precipitation intensity, but not duration, if that is the question.
I think there was, I think our volunteer assistant had a question for Robin, I think. Go ahead.
Yeah, I have a quick question. I'm quite interested in whatever you're doing, but as far as if those variables are quite independent each other, like temperature, wind, precipitation, I think it's quite hard to differentiate one to another. And let's say if you have like a good relationship between ozone and temperature, which ozone layer are you talking about? How high is it?
We're talking about surface ozone here.
Surface. So as far as atmosphere is considered, it's not really easy to limit whatever to surface, because you also consider whatever under the ground, as well as you're affected by above the ground, like temperature or whatever the wind, or like those troughs, like shortwave troughs or whatever happening above mid-layer kind of thing. So maybe you need to think about that kind of thing as well. And I'm quite doing lots of simulation related with GCMs from CMIP 5, CMIP 6. So I think the previous question was like the relationship between whatever you've got from 4 years can be applied to the future scenario. So like if there's a lot of temperature change, as well as changes of humidity as well, the relationship can be changed dramatically. So if you have like a relationship between 4 years and you try to apply it to 30 years, I think it can be a bit questionable. So, and you also need to think about like spatial and temporal resolution, because those are changing dramatically based on how you design or like the resolution. So maybe.
Yeah, absolutely. So I mentioned when I was showing those results for the future, that was just a proof of concept. So I am absolutely aware that using 4 years to extrapolate to 60 is not appropriate. And I don't intend to publish any results until I have the full set of simulations, which are going to span 40 years of time series, before I try to apply that to predicting the future. This was only intended to be a proof of concept, and I don't know if any of the results that I showed on that last slide are going to be robust. I don't guarantee it, and I don't believe it, and I wouldn't publish that. It's only intended to show the method. As to the horizontal resolution, so what I'm working with for the climate data has been first downscaled for regional modeling to be looking at the region of Canada in general. And in order to make it match the resolution of the GeoSChem simulations, it's actually had to be made more coarse than what the original data was. So I believe that a bilinear interpolation was used to scale it from the finer resolution of the regional climate data to the coarser resolution of the MERA-2 reanalysis data that's used to drive GeoSChem.
I think we probably,
Yep.
we
It's
just,
the time. Yeah.
we need to continue on at this point. So we'll go to our next speaker. Mark, do you want to do
Yeah,
that?
thanks to everyone for the, I hope people got
Very interesting.
some
Yeah.
health break in there, some interesting discussion as well. So our next speaker is Quiren Yu. Said that right?
It's fine. Sure. It's,
Okay, close. And title is an analysis of the global distribution of aerosol direct radiative effect and its implications for meridional energy transport. So anytime you're ready.
Okay, so good afternoon, everyone. My name is Qiu Run, and I am a PhD candidate from McGill University under the supervision of Professor Yi Huang. Today, it's my great pleasure to virtually be here and to present some of my ongoing work about the global distribution of aerosol direct radiative effect and its implications for meridional energy transport. So aerosols are microscopic particles suspended in the air. They can directly scatter and absorb the incoming solar shortwave radiation. Aerosol is important because they can modify the Earth's radiative energy budget and thus change the climate. This is the so-called aerosol direct radiative effect. And as you can see here in the figure, this is the global distribution of the all sky and clear sky aerosol direct radiative effect pattern. The most dominant feature is that this ADRE effect is super inhomogeneous on the global scale, and both the sign and the magnitude of ADRE varies a lot from region to region. So why is ADRE so complicated? Because there are many factors that can impact the ADRE value. First of all, the aerosol-related factors are important. For example, the aerosol radius, the size, the concentration can change the ability of aerosol to interact with radiation and thus change the ADRE value. But this is not the whole story. The environment factors such as the cloud fraction, the cloud optical depth, the surface albedo, and the solar zenith angle can also modify the ADRE value. Apart from running a radiative transfer model, there have been some studies that propose empirical methods to represent the ADRE value by deriving it directly from some important variables. For example, Haywood in 1995 calculated ADRE by using some variables such as atmospheric transmittance, solar constant, cloud fraction, and surface albedo. And these studies can allow us to gain the understanding of the sensitivity of ADRE to all these important variables. But there have been very few studies that truly separate the aerosol-related factors from the environment-related factors and study their impact to the ADRE spatial patterns. Moreover, because ADRE can also induce the meridional energy transport and the effect from different factors that contribute to this meridional energy transport still remain unclear. So with this background, we proposed some questions about our study. First of all, we wanted to know what are the major factors that can determine the global ADRE spatial patterns, and how much do they contribute to the meridional energy transport? And we wanted to know if we are given the trend of these important factors, can we know how much do they impact the trend of the meridional energy transport? So with these questions in mind, here are some data and method we used. So we used 22 years of Mero-2 reanalysis data, and the time period is annual mean. And for the method, we use a weighted least square regression. So the equation here shows the form of this regression model. Basically, we use some predictors, which is X, to predict the ADRE value. And here, because insolation is the most important factor to ADRE, so we normalize it. We normalize the ADRE by insolation. And after some tests, we find that the predictors we are going to use are as shown in the left figure, which is the aerosol optical depth, the surface albedo, the cosine solar zenith angle, and the cloud radiative forcing normalized by insolation. So with these predictors known, we can predict the ADRE value at each grid point. And here is the behavior of this empirical model. So the two figures, they are the clear sky case and all sky case respectively. The form of this regression model for the clear sky case is as long as we know three predictors, which is the aerosol optical depth, the cosine solar zenith angle, the aerosol optical depth times surface albedo, then we can successfully reproduce the global ADRE pattern. And as you can see from the scatter plots, the 95% of the variance in the global spatial distribution of ADRE can be explained by this regression model. And for all sky case, apart from the previous three predictors we used, we also add the aerosol times cloud radiative forcing term to indicate the cloud and aerosol's coupling effect. So these terms, they are important because each term can represent individual processes that are important when aerosols are interacting with the radiation. For example, for the albedo or for the LD term, it means how light can be directly scattered back to the space by the aerosol layers. And for the cosine theta term, it will indicate the path length that photons actually travels through in the atmosphere. And as for the albedo times LD term, it can indicate the multiple scattering effect between surface layer and the aerosol layer. And similarly, for the LD times cloud radiative forcing term, it can indicate the multiple scattering effect between aerosol layer and cloud layer. So with this empirical model successfully built, it will not only allow us to reproduce the global ADRE value, but also help us to understand the sensitivity of ADRE to different predictors. So here in the left figure is the clear sky ADRE sensitivity to the two predictor, which is the surface albedo and the aerosol optical depth, while the right figure is the all sky ADRE sensitivity to the three predictor. And for the conclusion here is that as for the ALD sensitivity, if the ALD is increasing, then over the low surface albedo region, the ADRE value will decrease. If the ALD is increasing over the high surface albedo region, then the ADRE value will increase. And as for the sensitivity of surface albedo to ADRE, it's always positive, and the sensitivity of cloud radiative forcing to ADRE is always negative. And it's also worth to mention that on the right-hand side in the each figure, the number indicates the global mean sensitivity of these predictors to ADRE. Let's just take the clear skies albedo sensitivity as an example. The 26 indicate that if the surface albedo were to increase by 0.1 globally, then the clear sky ADRE would increase by 2.3 watts per square meter. And apart from allowing us to understand the sensitivity of ADRE to both aerosol-related parameters and the environment-related parameters, this regression model is also a useful tool to help us understand how this term contributes to the ADRE and then further contribute to the meridional energy transport that ADRE induced. So the solid line here in the figure indicates the zonal mean ADRE pattern and the forward energy transport it's induced for clear sky case. So the different color dashed line indicate the contribution from different terms. And the conclusion here is that in terms of zonal mean value, when the aerosol optical depth peaks, it will not necessarily lead to the peak in ADRE because there will be mitigation effect from the aerosol and surface coupling. And it's also worth to note that in the Arctic region, although the aerosol loading is quite small, but because the surface is too bright, so the aerosol and surface coupling effect will lead to a positive ADRE value there. And because in general, Northern Hemisphere are more polluted, so the hemispheric difference in AOD will cause a cross-equator energy transport, which is around 0.2 petawatts. And as for the all sky case, we can still have a cross-equator energy transport due to the hemispheric difference in AOD. But because in general, the existence of cloud will mask the effect of ADRE. So the forward energy transport value will decrease, which will become 0.12 petawatts. And similarly, we also have the aerosol and we also have the strong aerosol and surface coupling effect dominates the Arctic region. Apart from understanding how these different terms can influence the meridional energy transport, we are also curious about how the trend of these predictors can influence the trend of the meridional energy transport. So here is the trend of the 22 years data for the clear sky aerosol direct radiative effect and its corresponding forward energy transport trend. So for clear sky, the trend of ADRE is basically caused by two variables, which is the trend of aerosol optical depth and the trend of the surface albedo. And we can find that the blue line, the black line and the red line, the two are very consistent with each other, which means in general, the AOD's trend will dominate the ADRE trend globally. However, there are some exceptions. For example, in the Arctic sea ice melting region, we find that although the AOD terms trend will lead to a positive ADRE value, but in the end, the total ADRE trend is negative, and this is due to the strong albedo trend there. So this effect will reduce the equator energy transport in the Northern Hemisphere. And this is the conclusion from the clear sky case. We also conduct similar trend analysis to all sky case. And because now it's all sky case, so we need to consider the trend caused by the cloud radiative forcing trend. And it's interesting to find that in the Southern Hemisphere mid-latitude region, the trend
just a quick warning, 3 minutes left.
The trend of the cloud radiative forcing will lead to an increasing ADRE trend there. And similarly, because there are strong albedo trend in Arctic sea ice melting region. So we also have a peak here, but because at the same point, for the all sky case, there are also strong trend in the cloud radiative forcing there. So this will mitigate the original large trend caused by the surface albedo. And also for the all sky case, the decrease of the hemispheric difference in AOD will reduce the cross equator energy transport. So here is my conclusion. First of all, to answer the first question, we know that the aerosol optical depths, cosine solar zenith angle, the surface albedo, and cloud radiative forcing are the major factors that determine the global ADRE spatial pattern. And we find that the hemispheric difference in aerosol emissions will cause a cross-equator energy transport. And this transport can be mitigated by the aerosol surface and aerosol cloud radiative coupling effect. And finally, we find that the AOD trend will dominate the trend in ADRE, except for the Arctic sea ice melting region and the Southern Hemisphere mid-latitude region under all sky case. So that's all I want to share with you today. And thank you so much for your attention.
Okay. Thank you very much. So I think we have time for one quick question. If there's one from the audience. Okay, I'm not hearing any unless someone's has unmuted. Okay. I had a very fast one. I was just wondering, you know, for your approach that you're using, you know, have you considered comparing to sort of a brute force approach for the sensitivities? Like you sort of have I think it looks a bit like a linearization equation, and I'm wondering how that compares to something where you actually run a model in a separate setup.
Yes, there have been some study that calculates the radiative kernels for each variables by using radiative transfer model. And we did compare our study with them. So first of all, for the pattern, it's very close. Like our study is positive, there is. But for certain regions, the magnitude of the sensitivity of our study is not consistent with them. But there can be many factors that contribute to this. Yeah.
Okay, thank you. I think we should move on to the next speaker then.
Okay, thank you.
Okay, next up we have Rachel Shang from Dalhousie, and presenting aerosol chemistry and physical properties during the Halifax fog and air quality study. So whenever you're ready.
Thanks. Can everybody hear me?
Yes, we're good.
Great. Thanks very much for giving me the opportunity to come and tell you about some of the measurements that we made in Halifax a few years ago. I have to admit that the analysis didn't get far enough to really link it to meteorology, but I'll show you what we're hoping to do. Okay, so first off, I wanted to acknowledge all the people who were part of this study. From Environment and Climate Change Canada, Wanmin Gong, and then from St. Mary's University, Aldona Viacek and Cameron Power. From York University, Cora Young, Trevor Vandenboer and their group. And then the people from Dalhousie University who actually did the work, Baba and Joel and Christian. This is most of the crew on top of the roof at St. Mary's. So the reason I'm really glad that I went after Shirun, because where she was talking about the aerosol indirect effects, direct effects, I'll be talking about why I'm interested in particles, but from an indirect effect. So as you likely know, particles can either nucleate from gaseous precursors into the atmosphere, or they can be directly emitted from primary sources. And in a coastal location like Halifax, the emissions that we're most interested in, or not most interested in, but the primary particles that we're partially interested in are sea spray aerosols coming from the ocean. And then if the conditions, once in the atmosphere, the particles can activate and grow, they can get processed and then they can grow. And if the conditions are right, they can turn into cloud or fog. They can basically just absorb water and grow activate into droplets, liquid droplets. And of course, clouds or fog can affect radiation by reflecting incoming solar radiation. So some of the questions that I was hoping to address with the study are things like, what are the droplet properties that are there? How do droplet properties affect visibility and albedo? Which aerosols actually activate into droplets? Where do the particles come from? Unfortunately, the analysis that I'll be showing to you today is skimming the surface of where do the particles come from, and then also what are the droplet properties. Haven't been able to quite link everything together yet. So the study, which we cutely named Halifax, is the Halifax Fog and Air Quality Study. And it took place at St. Mary's University, which I show with a star here in Halifax in the southern peninsula of Halifax. And we were interested for fog and air quality, partly because there's a large shipping terminal right in the southern part of Halifax, just not too far from our site. But we're also influenced strongly by fog in the spring season. So we had two phases of our study. The first part was what I called the intensive study between May 28th and June 25th in 2019. And in this part of the study, the unique instruments that were part of the study, were ozone NO, NO2, but also HCl in the gas phase. And then the group from York brought a nano Moody, which measured the size resolved as aerosol chemical composition, the soluble component of it. And there were solar radiance measurements. And then for an extended period until August 27th, so starting May 28th and ending until August 27th, there were other additional gaseous gas measurements conducted by Aldona Viacek's group using an open path FTIR system. These are some of the gases that have been retrieved so far, but there are other potential gases that could be studied in the future. My group conducted aerosol measurements in terms of measuring the size distribution between 0.01 to 3 microns, CCN concentrations, which unfortunately have not been analyzed yet. We had an ACSM, an aerosol chemical speciation monitor, which measured the bulk non-refractory aerosol chemical composition and fog droplet size distributions. And so I just wanted to show you a photo of our site. Here is the nano Moody measuring aerosol, so the soluble component of the aerosols. The fog droplet monitor down here. There are additional instruments. The open path FTIR was pointing outside of this window. Here we are inside the container with the the aerosol equipment and additional gas phase gas instruments, which hadn't moved in yet when this photo was taken. I'm going to point out this kitchen exhaust, which was really close to our site, unfortunately, which I think contributed to some of our observed aerosols. Just wanted to quickly start by showing the aerosol size distribution and concentrations that we measured throughout the study. Unfortunately, our instruments, there was a leak in our inlet until June 17th. So the data that I'm showing you occurs after that. This figure, if you're not familiar with it, in the background, in the colored background, is the size distribution. So aerosol size on the y-axis and date on the x-axis, and color shows the normalized concentrations. So you can see that there are particles small, but then growing quickly to larger sizes. That occurs, like this growth pattern occurs several times. But mostly the particles that we see are below 200 nanometers, which is denoted by this line here. The top figure shows in white the total particles counted by the SMPS, so that's below 500 nanometers, and then various fractions measured at the larger sizes. I'll zoom in onto other portions later. I also wanted to show quickly the non-refractory aerosol chemical composition measured by the ACSM throughout the study. And the bottom figure shows the inorganic masses, nitrate in blue and sulfate in red, and they correspond to the left axis over here. And then the green is the organic mass concentration is determined by the instrument. And it has a different scale, which I'm showing you here on the right, and it's almost 5 times higher in general than the inorganics. And so it's really interesting because this seems to be quite consistent in Halifax, that most of the aerosols that we observe are strong or are almost primarily organic, at least measured from this instrument. And then this is a poor person's PMF, so just trying to do a factor analysis based on specific peaks of the instrument. And I'll maybe zoom in on this later and describe it in greater detail later too. And then I just wanted to also show the size resolved soluble chemical composition measured by the nano Moody. This figure is taken from a manuscript that's been accepted by Environmental Science and Technology. But the top figure shows the size resolved portion of the total ion concentrations. And so 1 micron is this line here. And so you can see that in the coarse mode, I'll start in the coarse mode here on the right, most of the ions are, most of the aerosols composed of sodium in light blue and chloride in orange. So it's the cations on top and the anions on the bottom, with some indication of aging from nitrate shown on the bottom. But at the smaller sizes, it's mostly green, so ammonium as for cation and nitrate in the anion. And this is the bottom figures show the percentage breakdown. And so you can see in the accumulation mode between 0.1 micron and 1 micron, most of the aerosol is ammonium and nitrate and sulfate. Well, sulfate more and some chloride. But in the coarse mode, it's definitely mostly chloride and sodium. And one of the calculations that Yutao did as part of this study was to determine that the pH of the aerosol is approximately 3. So the aerosol is highly acidic, and that the particles smaller than 500 nanometers were more acidic than the coarse mode aerosols. I tried to analyze because of the large organic mass fraction or organic fraction that really made up the aerosol. I was interested in trying to understand where the organics were coming from, because it is really strange that we consistently see like a strong organic component to the aerosols. And so here I've zoomed in on a week, or I guess 11 days in June. Sorry, at the beginning of this time series. And so in this pink figure on pink line on the top, it shows the oxygenated organic aerosol, or OOA. In the gray, it shows the hydrocarbon-like organic aerosol. And so sorry, I should have back up and say that the OOA is supposed to represent a secondary organic aerosol type character, whereas the gray is more like a primary organic aerosol, so directly emitted from likely vehicles. And then this brown is an indication of the biomass burning organic aerosol. But I think we could generalize it more to other types of burning, for example, like from a stovetop that is potentially coming from the stove or kitchen exhaust on the first floor of our building. So I just looked at the organic mass spectrum at these 3 times. So this period here on June 17th looks like it's more like a regional influence, like a slowly building organic aerosol, whereas this period right here on June 18th is just this spike of gray and pink, so primary and secondary organic aerosol with looks like a small contribution from the burning aerosol. And then you can see this gray spike here on June 19th, which is likely coming from a primary organic aerosol source. And so if we look specifically at the mass spectrum for these 3 periods, you can see that there's distinct differences. This regional, more regional aerosol on June 17th is really similar to that of what we would expect from an oxygenated organic aerosol. Indeed, as the pink line was suggesting, the bottom, the last peak, as we also thought, is likely the mass spectrum really looks like that of a hydrocarbon-like organic aerosol, so primary organic aerosol. And then this middle one, it's really interesting. I showed this to a colleague, and they looked at it and it's like, oh, it really looks like cooking aerosols. And so sorry, I should go back to here. It's maybe not that surprising. There is a small spike in the BBOA, suggesting that maybe we really were being influenced by cooking. So it wasn't what we were looking for, but that's what ends up happening sometimes. I just wanted to point out one more thing about this time series, which is that at first it seems like there's a really strong weekday weekend signal in our data. So this is a period in August, and August 12th was a Monday. And you can see it looks like there's these strong spikes in the organic mass that typically happens in the middle of the day. This is in Atlantic Standard Time right now.
Just to let you know, 3 minutes.
Okay, thanks. Whereas the signal is much weaker on the weekends. And I'll just point out that at first I thought that this was all just kitchen exhaust, but it turns out it's not quite true. I think based on the size of the particles, these two spikes are different than the rest of these. I think these ones are probably anyways. So that's the story there. And interestingly, what was the poor person's PMF factor analysis couldn't really account for all the variation in the organic signal. So there's definitely something further to examine here. Just wanted to quickly wrap up with the fog. So I haven't been able to link the two yet, but we also looked at the fog droplet size distributions, and our fog tended to be bimodal in nature, with our summer fogs tending to be having more large droplets, which reduce visibility, increase albedo, versus our springtime fogs, which had more smaller droplets. And we think that the springtime fogs are more likely to have precipitation and that the air is more coming from marine sources. So I'll leave it there in summary, with some future work for you to look at. Thanks a lot.
Great, thank you, Rachel. So we have about 1:30 people. If you have any questions, just speak up.
Can I ask then, Rachel?
Yeah.
If I'm curious, like I'm sure there's information about wind speed and wind direction. So like looking into where the sources are coming from, how much would that factor into this analysis?
Yeah, I haven't looked at just the aerosol data with the wind yet. I've really been focused before this on looking at the fog. And trying to understand wind patterns with fog, because that was the most obvious link. But that's, I mean, I can tell you that the winds are predominantly from the southwest, generally speaking, just at our location. Okay. But there are some changes in wind pattern coming from the east, especially in the early part of the study.
Does the fog typically come off the water?
Yeah, I mean, it's hard to determine what's off water or on water because we're on a peninsula.
Yeah.
And then exactly what part is, when is it on the water? How much land do you have to cross before it's no longer considered water? So these are definitely things we're trying to work out still.
Yeah, tricky location.
It'll be interesting to see. I was thinking the same sort of thing. Actually, Mark, the particle nitrate. Is that associated with long range transport from New York or something like that?
Mm-hmm.
Anyway, oh, sorry, just keep an eye on the time. We should probably go on to the next speaker then. Thank you very much.
All right, thanks. So our final speaker for this session is Jack Chen from Environment Canada, who will be presenting recent research on Canada's firework wildfire air quality forecast system and 2021 fire season's impact on weather.
Okay. Okay, I just share my screen and I'm muted. And am I good to go?
All good.
Yes, good to go.
Okay, great. Thanks. Actually, I guess it's nice to be at the last talk of the session because Chiron and Rachel talked about aerosol direct and indirect effect. And here I'm actually going to demonstrate some of those in our air quality forecasting system. And this is the firework system from Environment Canada. And this is work in collaboration with a lot of people, including our colleagues at the Canadian Forest Service Natural Resources Canada. Next slide. So 2021 was the worst fire season in the recent decade. Here I'm showing the burn area across Canada from 1980 and 2021. We had more than 4 million hectares of forest that's was burned, more than 6,000 fires, and thousands of people evacuated, buildings destroyed. And most of the fire happened in provinces of British Columbia, Saskatchewan, Manitoba, and Ontario. And here I'm showing the area burned compared to the 10-year average. And as a result of all these fire activity, there were really significant degradation in terms of air quality on the surface. Here I'm showing surface PM 2.5 measurement from several NAP stations across the country. And so the red is hourly measurements, and the blue dotted line is the is the Canadian MBI air quality standard, and this is 24-hour average at 28 microgram per meter cube. So for the month of July 2021, what we're seeing here is there are several occurrences of PM2.5 exceedance of these standard, and this is really a direct result of forest fire activity and smoke fumigating the city centers, and the impact really reaching out even to the East Coast, Nova Scotia. And so in sort of response to the increasing fire activity and degradation to air quality, Environment Canada started this 5-word air quality forecasting system since 2016. The system is actually based off our regional air quality deterministic prediction system, or RQDPS, which is our GenMAC chemical transport model that Roya just talked about earlier. And RQDPS has a full set of anthropogenic and biogenic emissions. And 5-word is basically wildfire emissions in near real time added on top of RQDPS. So on the right here, I'm showing a quick schematic of how we're getting the fire emissions into the modeling system. We get fire activity, so fire location, fuel type, and estimated burn area from the Canadian Wildland Fire Information System. And this is all created by NRCan. And then the information then gets fed into this Canadian Forest Fire Emissions Prediction System, or CFES, which then estimates the fire growth, activity, and emissions with forecast hourly meteorology. At the same time, it has the energy balance adjustments to calculate plume injection height. And all this then gets into our GenMAC chemical transport model. The system simulates 72-hour air quality forecast and twice daily. And over the years, 5-word has gone through several updates. And just most recently in December 2021, all of Environment Canada's forecasting system was updated, including 5-word. And one of the key updates to 5-word system is the update from CFES, earlier version to CFES 4.1. And the key update here is the closer interaction with meteorology. In this case, we have actually the research version has CFES coupled in our chemical transport model. And this allows us to really study the smoke aerosol couple interaction. So this with this setup, we study an interesting episode in July 2018, where there was a suspected daytime cooling due to wildfire smoke. Dave Phillips, our meteorologist, was quoted in saying temperature got up to 13.4 in Edmonton, but was forecasted to be 26 and 27. And part of the reason is because in our regional deterministic prediction system, our regional NWP, it has climatological aerosols, but it is not aware of the aerosols produced by fire that's happening in the region. So the shortwave radiation accumulation is not being properly captured. And here at the bottom, I'm showing the analysis minus forecast at that time for surface temperature. And here I'm showing approximately 5 degrees Celsius over prediction from our regional NWP. And this correlates quite well with total column PM2.5 from our 5-word system. So in the next couple of slides, I'm going to talk about 3 analysis from 3 systems. One's our operational 5-word system, and that's 5-word 022 that was operational at the time. And the second is our recently updated 5-word system, 5-word 023 with CFEPs, updated CFEPs. And then I'm going to compare that with our research version of fully coupled CFEP with GenMAC. And this is with GenMAC with feedback. And what that means is it actually accounts for the direct and indirect aerosol feedback, which was talked about earlier in the session. So here I'm showing surface temperature comparisons, just looking at the runs with feedback minus the runs without feedback. So here in the middle, this is average surface air temperature for the week of July 16th. This is daily maximum average, taking the runs with feedback minus the run without feedback. And what we're seeing here is that there's an average of about 0.1 degrees difference if we were to account for aerosol direct and indirect feedback in this simulation. And this is as a result of the aerosol within the atmospheric column attenuating the shortwave radiation reaching ground. And then the magnitude is certainly a lot larger if we were to look at hourly comparison. This here I'm showing for July 18 at 2 p.m. The surface temperature difference with feedback is up to about -8 to -10 degrees difference when we count for the aerosol direct and indirect feedback in the forecast simulation. And there is certainly very similar in terms of magnitude on the forecast UV index that is now currently also available in our forecasting system. And this is to show that the special distribution actually correlates quite well with the total column PM 2.5 that was simulated from our firewall system at the time. So what's interesting too is to really compare that with actual surface measurements. So here on the left, I'm showing Fox and Whiskers plot for daily maximum temperature on top and then daily minimum temperature at the bottom. And this is for the three forecast simulation, including observations. So observations is orange reddish bar, and then the two operational setup is in the middle, and the setup with firewall research with feedback is this purple one. And these are the three forecasting days. If you look at the third forecasting day, so the forecast hour for 48 to 72, what we're seeing is that the firewall with feedback actually considering aerosol feedback is really capturing the observed surface temperature reduction better compared to the operational runs without the feedback. And this is for all stations in Alberta. And if we're to focus on just stations in and around Edmonton, and here I'm showing about 11 stations in Edmonton, the magnitude difference is certainly much bigger. Here observations is close to about 22 degrees, and the operational system, operational firewall 022 at the time shows over prediction of surface temperature, and then the current operational system, the updated version firewall 023 shows slight improvement, and this is certainly due to the updated gem physics. But if we're to really consider the aerosol direct and indirect feedback in the research version, we see the forecast temperature is captured much better compared to the observations. And one thing to point out too, that in observations there is much bigger variability, and that is expected because our modeling system is a 10-kilometer grid, and we are certainly not capturing the observed variability at the time. So moving on to, this is a pretty busy plot, but I'm showing the air quality forecasting comparisons. And this is for daily maximum PM 2.5 for the month of July. And again, I'm comparing three different model setup with observations. And on the left, this is for firework operational at the time. So firework 022, that was operational at the time. And this is for all of the measurement stations in Alberta on top, in Ontario at the bottom, in the middle here, and Quebec in the bottom. And in the middle column here, I'm showing the current operational system that was recently deployed, and that is operating in this fire season. And on the right here, this is the research version considering aerosol feedback. So what we're seeing here is that in the then operational system, firewall 022, we are over predicting the observed surface PM2.5 by quite a bit in some of these locations. With a recent update with updated CFETs and GEM, we are correcting some of these over predictions, specifically in Alberta and to a certain extent Ontario and Quebec. But very interestingly and very encouragingly, that with the research version, the over prediction is really not being observed here. And this is I should stress that this is really in a combination of a lot of factors, including feedback, but as well as improvements in the changes in gem microphysics, as well as the use of 12-bin representation of aerosol compared to 2-bin representation of aerosol in the operational system. And the signal is actually quite clear as well if we look at the PM2.5 evaluation statistics. For
two minutes left. Sorry.
All right, thanks, Paul. So here I'm showing the overall comparing to all stations in Canada, and what we're seeing is that there is certainly an improvement in correlation coefficient and reductions in lumen square error. And here is just time series comparison for stations in Edmonton and Toronto. And what I wanted to show here is that we're really capturing the temporal onset quite well with this forecasting setup. So one thing that I wanted to also point out is fire weather index calculation. So fire weather index is fire risk index that is quite critical and is operational product from the Natural Resources Canada. And this is calculated using surface temperature, relative humidity, basically variables that are important for fire growth. And using the fire weather index calculation in GenMag with and without feedback, what we are showing in this experiment setup is that with changes in temperature, relative humidity, and to a certain extent precipitation as a result of aerosol direct and indirect feedback, we are seeing changes in forecasted fire weather index. And in this case, with decrease in temperature, there's reduction in the forecasted fire weather index as a result of the considering the feedback from aerosols. So very quickly, summary. So the current new setup, we're showing improvements compared to the operation, compared to the surface measurements. And in terms of development, we are moving towards setting up an aerosol feedback system and really trying to see if we can operationalize this application. One critical point is that it requires a 12-bin representation of modeling setup, and that really takes a lot of computational resources. So I guess I'm running out of time, so I want to stop here and take your questions.
Okay, thanks very much, Jack. I think we are right at the end of the time. Maybe we can have one quick question, if there is one.
There's a question in the chat.
Yep.
Is there somewhere to access the source data for the plot on slide 2 of the provincial area burn per year? And is this available on a monthly scale?
Oh, those were actually provided to me from the Canadian Natural Resources Canada, Canadian Forest Service, and I'm sure that's available. Yeah, send me an email and I will probably make the connections.
Okay, we'll leave the session open. We can turn off recording, but allow you guys exchange emails if you don't have it. Yeah, so thanks to everyone for great talks. It was a really interesting session. We'll continue in about 15 minutes with the last air quality session of the day. Hopefully everyone can make it back for that.
I think that also worth mentioning that there was another air quality session on Friday that's focused on the oil sands. That's session 2040.
Yeah, Friday morning. So yeah, so hopefully we'll see you again. So I guess, Yun-Sung, if you want to
No,
pause the recording and
yeah, you guys are free to leave, and I will just quit recording from now.
Sure.
Thanks.
thanks.
Thanks, everyone. Bye-bye.